So in this video, I want to answer the question, what is a differential equation? Um, Hopefully we'll be able to see in answering this question some examples and maybe get a feel for why one might care about differential equations. So what is a differential equation? Now, differential equations, this phrase is going to be used a lot, and you can see that it's got a lot of letters in it, so we're probably going to abbreviate this very often as DEs. What is a differential equation? What is a DE? Okay. Oh, and this is not English because I wrote what is a differential equations. So let me do this right. What is a differential equation is really the question that I'm answering here. Okay? And the answer is that it's an equation involving derivatives, which sounds really dumb. You know, that's what it is. So why try to make it more complicated than that? That's what it is. Now, why would one want to deal with such an equation? Well, remember, so recall, if f is a function, then we have various notations like f prime or df dx, assuming x is the independent variable here, for the derivative. Denotes the derivative of f. This is all Calc 1 stuff. And hopefully in your Calc 1 class, you learned one of the fundamental facts about interpreting this derivative. We interpret df dx, interpret the df dx as the instantaneous rate of change. Instantaneous rate of change in the values of f. Okay, so just to quickly review this, so for example, if you have that x of t, let me denote this differently. If you have that s of t represents the displacement of an object. So you have some object moving through space in some way. You can imagine it moving either along a one-dimensional line or maybe along in a two-dimensional plane. Either way is fine. Then you can imagine s of t being its displacement relative to the origin. So if you have some particle here, you could have some vector connecting this to this. That's going to be our s of t. All right. And again, this depends on time. So it's going to, I don't know why I said again. This depends on time. So you have to imagine this thing is sort of traveling around the plane in some way. Maybe it does something crazy like this. And for each of the various points along this this crazy movement, you can track its displacement relative to the origin through a vector like s of t. Some basic physics. Well, what would s prime of t be then? S prime of t would be naturally the rate of change of the displacement, which we have a name for. We call it the velocity of the object. This, remember, hopefully you remember, we think of as being something like a tangent vector to the curve in which this thing is traveling. This ends up being v of t, the velocity. Okay, and you can go even further and take a second derivative. In other words, the instantaneous rate of change of the velocity. And that, of course, is acceleration. And why stop there? There are higher order derivatives as well. They go by all sorts of very interesting names. Like the third derivative, I think, is called jerk. The fourth derivative is called snap. and the fifth derivative is crackle, and the last one is I forgot already. I think it's pop. Anyway, those are the derivatives, and a fundamental interpretation again, in general, which is very important here, is that if you have a function f, okay, if you have a function f, then f prime or df dx, either way, this is sometimes called prime notation. This is called Leibniz notation, named after the German mathematician Leibniz. You interpret those as being the instantaneous rate of change in the values of f. Very important interpretation, that, okay? And it's one that all mathematicians, scientists, engineers care quite a lot about, and hence the reason that they care about differential equations, because differential equations are things which are going to give you ways of describing these instantaneous rates of change. Let me give you an example using what we just learned of DEs. So Newton's second law is a really good example. F equals ma. You've hopefully all seen this before in your life. This is a differential equation because acceleration, which is what A here stands for, is the second derivative of something. It's the first derivative, by the way, of something as well. So that we could just as equally write this equation as a differential equation, F equals m times dv dt. That's a nice way of writing it. But we could equally well write this as F equals m times d squared s dt squared. Yeah? And in writing this this equation F equals ma in these two different ways, we really bring out the its nature as a sort of description of how something is changing. In the case of acceleration, we're talking about how acceleration is changing. And in the case of going from this sort of representation to this sort of representation, well, we're sort of seeing how, sorry, I can't do that with this iPad. In seeing how it goes from this kind of representation here into this one, we're sort of saying how it is that the force is somehow related to the way in which the rate of change of the rate of change of position. It's sort of related to that, yeah? That there is this relationship. That's Newton's second law, which he discovered empirically. Another example of a differential equation might be something like a radioactive decay. So maybe you know, if you have, particularly if you have a highly radioactive material, if you have a pile of that material, it will naturally decay with time. That is to say, bits of it, like if you have uranium, some isotopes of uranium are highly radioactive. If you have that lump of uranium and you wait a little while, you're going to have only a portion of that material left because the rest will have decayed into various subatomic particles and shot off into space, and you'll no longer have it in your little pile of uranium any longer. This phenomenon is called radioactive decay. And it's of great interest to physicists, chemists, people who care about radioactive materials. And they have differential equations to model the amount of stuff, of radioactive stuff, at a particular time t. So if you call the amount of stuff, you call that m of t, then we have the following relationship. Maybe dm dt is equal to negative lambda times m. In other words, this is saying that the rate of change in the mass of this radioactive lump of stuff, the rate of change of it is proportional, negatively proportional. So imagine lambda is a positive number here, so that negative lambda is a negative number, is proportional to the amount of stuff present. The more stuff that you have, the greater the rate of change, the greater the amount that will decay will be, right? This will lead us to being able to calculate things like the half-life of radioactive isotopes and that sort of thing. So it's very, very useful. It's useful in particular for like carbon dating. There's something called radiocarbon dating in which you use an isotope of carbon. I believe it's C14. Usually carbon has 12 thingers around it. C14 has 14 thingers around it, and I guess it's radioactive. It's unstable, and it has a particular half-life. And so you can use that half-life to date certain organic materials that you find, and that's useful for like archaeology and anthropology and that sort of thing. So that's cool. That's another differential equation. As you can see, it involves a derivative. See, there is a derivative right there. Okay, cool. Another example which I want to highlight is something called the heat equation. Okay. This one is the following. If you have, imagine you have a bar, okay? A bar, and you have at each point in that bar some heat, some amount of heat in that bar, and you measure it. And we call Ux of T. So U is going to be the measurement of the heat at position X along the bar at time T, okay? So now we're talking about a function U, which eats two inputs. So we're in Calc 3 territory. We're in multivariable calculus territory. It turns out that there is a relationship between the partial derivatives of the heat in this bar. It looks like this. Partial, let me do that again. Partial U, partial T. So the time, the rate of change of the bar at time T is equal to K, with respect to time, is equal to K times the second derivative, partial U, partial X squared. So T here is, let me be clear, U of xt, okay, is the amount of heat in a bar, and I'm assuming the bar is sort of one-dimensional, so you might imagine a long, rod or something like that. So it's the amount of heat in the bar at position X and time T. And I bet you can understand why that might be of physical interest to people like physicists or engineers, right? Trying to understand how the heat inside of a bar evolves with time, okay? This is what's called a partial differential equation for maybe obvious reasons. This is abbreviated PDE often. And it's a subject unto itself, and it's very, very difficult and very, very sophisticated and interesting. Whereas these equations here, this one, these are called ordinary differential equations. We're going to talk about all of this more in future videos. This one's also an ordinary differential equation, an ODE. Okay. But this gives you a sense of the kind of flavors. There are lots of phenomena in the universe which are modeled by ODEs, but there are also phenomena which are measured by and modeled by partial differential equations. Heat equation is only one. There's also something called the wave equation. There is something called Schrodinger's equation, which tells you about the evolution of the quantum wave function of quantum systems, and it's all very, very interesting. We will have occasion to understand the solutions to all of these. But what I want to talk about in the next video is what does it even mean to solve a differential equation in the first place, okay? Hopefully you've come away from this video at least with an understanding of what differential equations are. They are equations involving derivatives. You understand why we might care. It's because we care very much about the rates of changes of things things in the universe are changing all the time, everywhere. Change is just the normal thing. So if we want to understand the universe, we got to understand change. And the best way to understand something is to make it mathematics, okay? Is to model it using mathematics. Well, best way of understanding. Maybe the humanists will kill me for that, but I don't care. We see this very important example of derivatives coming into play in mechanics. And then we have these examples here of differential equations, both ODEs and PDEs. Okay, that's enough for this video. See you in the next one.